Hello and welcome. In this video, we're going to be taking a look at rational functions, and that's where you have a polynomial in the numerator divided by a polynomial in the denominator. Now, we spent a lot of time in pre-calculus figuring out how to add, subtract, multiply, and divide rational functions. But in this video, we're going to be doing something that seems a little bit backwards. Instead of adding several rational functions together, getting a common denominator and expressing it as a combined rational function, we are going to be taking a rational function and splitting it up into smaller or simpler little rational functions. That process is called decomposition into partial fractions. Now let's start off with the basic theory of how we add rational functions together. If we have something like 3 over x minus 1 plus 4 over x minus 1 squared plus 12x plus 5 over x squared plus 3, the first thing we're going to need to do is get that common denominator. Now we always strive to get the lowest common denominator. So you see that in one of these expressions I have x minus 1, and in another one of these expressions I have the denominator x minus 1 squared. Well, okay, then I'll definitely need to make sure that I have a common denominator of x minus 1 squared, but I don't need to have x minus 1 cubed. My third expression has a denominator of x squared plus 3, which is certainly not a factor of any of the other denominators. So my lowest common denominator is also going to have one single factor of x squared plus 3. I wouldn't want to have any additional factors because that wouldn't be the lowest common denominator. Now it's simply a matter of getting equivalent rational expressions with that denominator so I can add them together. And I can always take a rational function and multiply numerator and denominator by the same non-zero expression. So for this first rational expression, I need to multiply by another factor of x minus 1, and I need to multiply by a factor of x squared plus 3. I'll have to do the same thing to the numerator. For my second expression, I only need to multiply numerator and denominator by x squared plus 3. For my last rational expression, I need to multiply numerator and denominator by x minus 1 squared. Now that I have everything over a common denominator, I can write this as a single fraction. Now you'd be able to expand the numerator and collect like terms, but here's the basic idea anyways. We need to get that common denominator so that we can add up all of these small rational expressions into one. But now we're going to be taking a look at taking a rational function and decomposing it into partial fractions, which is exactly the opposite. To get an idea, let's suppose that we had any kind of polynomial p of x. Is it possible to take p of x over x minus 1 squared times x squared plus 3 and write it out as a sum of the same sort of three smaller rational expressions? Let's start off with one specific kind of case where we can take a rational expression and simplify that into several smaller terms. Let's suppose I simply have the rational expression x cubed minus x over x minus 2. Well, what if I wanted to simplify that into simple, separate terms? Well, because the polynomial on the numerator has a degree of 3 and the polynomial in the denominator has a degree of 1, we should actually be able to perform long division of polynomials and split this up into separate terms with the quotient and remainder. With long division, we're going to divide x cubed minus x by x minus 2, or x minus 2 needs to go into x cubed minus x. Now, it's going to be a lot easier if we actually take a look at all of the zero terms as well. So I will write in a plus 0x squared and a plus 0. Now, the first thing I'll start off with is really just taking a look at this leading term x and see how many times it goes into the leading term x cubed. Well, we can perform that division, x cubed by x, and we end up with x squared. So x minus 2 will need to be multiplied by x squared. That gives us x cubed minus 2x squared. And we will subtract to see what the remainder is. X cubed minus x cubed ends up 0, and 0 minus negative 2x squared becomes 2x squared. We can pull down the remaining terms, minus x plus 0. And we will look again at this leading term, 2x squared, and see how many times x goes into 2x squared. We will look at 2x squared divided by x. Well, that gives us 2x, and that will be the next term of our quotient. And we will need to take x minus 2 times 2x. That gives us 2x squared minus 4x. And we'll have to subtract to find the remainder. 2x squared minus 2x squared is 0. Negative x minus negative 4x is positive 3x. and we'll continue to bring down the 0. And we'll have to look at the next leading term, 3x. Finally, we're starting to get rid of x's. 3x minus x is simply equal to 3. We must be getting pretty close to the end here. Take our x minus 2 and multiply by 3, and we have 3x minus 6. And when we subtract, we'll end up with a remainder of simply 6. And there is no way that we can take 6, divide by x, and continue to do long division at this point in time. We always stop when we reach a remainder with a degree that is less than the divisor. Our divisor is linear, x minus 2, and we have a degree which is less than 1 now, so that stops our division. Now, we should be able to write our rational expression in terms of its quotient and remainder. When we perform the division, x cubed minus x by x minus 2, we have a quotient of x squared plus 2x plus 3, and a remainder of 6. So we write 6 over x minus 2. And so you can see we do have a much smaller rational expression that we are working with, and we have separate terms, and these are in fact not even rational expressions. That's just simply a polynomial. But that is a very quick way to take any sort of rational expression where the degree of the numerator is greater than or equal to the degree of the denominator and split it up into some smaller partial fractions. Now, assuming that the degree of the numerator is less than the degree of the denominator, we need to somehow establish what kind of partial fractions we'll get when we try to decompose the rational expression. We'll need a small but very important theorem regarding factoring polynomials, and that's that every non-constant polynomial, that means any polynomial with a degree of at least 1, can be factored into a product of linear and irreducible quadratic factors. Now remember, a linear factor would be a factor of the form ax plus b, with a and b being real numbers. A quadratic factor would be any factor of the form ax squared plus bx plus c, where a, b, and c are also real numbers. And we say a quadratic is irreducible when we cannot factor it into two linear factors with real values. Remember that in the quadratic formula, we have the discriminant b squared minus 4ac inside the root. And in the case where b squared minus 4ac is negative, we cannot factor that quadratic into two linear factors with real coefficients. Now keep in mind that some of these factors may be repeated, so we can have any linear factor possibly to a power of n if that factor appears n times. All right, with that in mind, there are only so many different kinds of factors we can have, and there is a nice form for the kind of partial fractions we will get depending on how the denominator can be factored. Starting off with a rational expression, p over q, where p and q are polynomials, where the degree of p is less than the degree of q, we will factor q completely into linear and quadratic factors, which may or may not be repeated. For each factor of that denominator, we will set up the corresponding partial fraction forms. So let's start off with a factor that is simply linear. For a factor that is linear and not repeated, something that just looks like ax plus b to the power 1, then for a partial fraction, we can expect the denominator to be ax plus b with a constant in the numerator. Let's call that capital A. Now, if we have a linear factor that is repeated, that would be something of the form ax plus b to the power n, for n greater than 1. Well, in that case, we will have to have multiple partial fractions set up. Very similar, we will have a constant over ax plus b. But then we can also have fractions involving ax plus b squared, with another constant on the top. So why don't we start labeling our constants with numbers? Constant a1, and this would be a2. And we will continue to raise the power of ax plus b in the denominator one partial fraction at a time until we've reached n. And so our last partial fraction would be a sub n over ax plus b to the power n. Now remember that when we factor the denominator, it's possible that we have irreducible quadratic factors as well. In the case of an irreducible quadratic factor that is not repeated, then we would have ax squared plus bx plus c to the power 1. And our partial fraction form would also have the denominator ax squared plus bx plus c to the power 1. Now the numerator here is just a little different. The numerator is actually always just going to be 1 degree less than the degree of the denominator. So on the top here, in our numerator, we should have the potential of a linear expression, ax plus b. And a and b are going to be constants. Not the same a and b as what we have in the denominator here, so we'll use capital letters, capital A and capital B. Last but not least, it is possible to have an irreducible quadratic factor in the denominator that is repeated. That's where we'll have something of the form ax squared plus bx plus c to the power n, where n is greater than 1. Much like our repeated linear case, we will have to have a series of partial fraction forms with the powers of the denominator increasing from 1 to n. And since there are no other cases of potential factors in the denominator, these are the only partial fraction forms that we'll ever need to use in order to figure out how to decompose our rational expression into these partial fractions. Now that we have these partial fraction forms, let's see what the step-by-step process is for determining these coefficients and decomposing our rational expression into these partial fractions. Let's suppose we're given the rational expression p over q, where p and q are non-constant polynomials. Now step 1 is simply just going to be our long division. And this is only going to be useful in the case where the degree of p is greater than or equal to the degree of q. If that's not the case, then we'll continue on to step 2. But if we can perform long division, then we will, and we'll rewrite p over q as being equal to s plus the remainder r over q. And the degree of the remainder is now certainly going to be less than the degree of q, which is our divisor or denominator. It is quite possible after performing step 1 that we continue needing to perform our partial fraction decomposition on r over q. But when we are writing step 2 down here, we're going to be assuming that we start off with some rational expression p over q, where the degree of p is definitely less than q now. The first thing we'll do is we'll completely factor the denominator. Once we've completely factored the denominator, then we can set up the combination of all of the partial fraction forms. And those partial fraction forms are given by the table that we just looked at. In step 3, we're going to set our rational expression p over q equal to the sum of all of the partial fraction forms and solve for all of those unknown coefficients. And those would be like the capital A's and B's and so on in the numerator of each of those partial fractions. Now there are a couple different methods for solving for those unknown coefficients, but let's see if we can start off with step 2 in an actual example and see how we solve for that in practice. Let's decompose the rational expression x minus 5 over 2x cubed minus 3x squared plus 5x into partial fractions. And we're very lucky here that the denominator can be factored quickly with just a common factor of x. And you should continue to try to factor the denominator, but we'll find that that quadratic factor cannot be factored into any other linear factors. So we say it's irreducible. In fact, even if you were just to try to look for any real roots of the quadratic, you will find that the discriminant is negative. So there aren't any real roots at all. This is as far as we can factor, so we'll set up our partial fraction forms. For the first factor in the denominator, x, that's linear and non-repeated, so our first partial fraction form is going to be a constant over x. Now, our second factor here is an irreducible quadratic that is non-repeated. So its partial fraction form is going to have the denominator 2x squared minus 3x plus 5. But for the numerator, instead of ax plus b, we're going to have to shift down the alphabet and go with bx plus c since we've already used capital A. Now it's this equation here that we need to solve for the three coefficients a, b, and c. And it's going to seem a little bit weird. We have to solve for three unknowns, but we only have one equation. Usually you're going to have 3 equations to solve for 3 unknowns. Now there is a way to take this equation and actually come up and derive 3 separate equations from it. And there's really a couple different methods we can use. Let's take a look at a method that I think we'll probably use in this case and will work in general, but I'll also show you a very quick shortcut that will also work maybe a little quicker in some certain scenarios. So what we'll do immediately is we'll make this equation easier to look at by multiplying by a common denominator, which is actually just this denominator on the left-hand side. When we distribute x times 2x squared minus 3x plus 5 onto each of these separate rational expressions, we should just get the polynomials in the numerator multiplied by any factors missing in the denominator. So this first example, x minus 5 over the denominator multiplied by that denominator will just end up being x minus 5. But this second rational expression, a over x, when we multiply by x, x's cancel, and we'll have just a times 2x squared minus 3x plus 5. And then this last rational expression, the quadratics are going to cancel, and we should just have the numerator bx plus c multiplied by x. At this point in time, we don't have to worry about any denominators. There are no more rational expressions, and we can start expanding things out. In the first method that I'll show you here, I'm going to expand out and collect terms. So I'm going to collect all of the terms that involve x squared, all of the terms that involve x, and all of the constants. On the left-hand side, there are no x squared terms, but I'm going to write 0x squared just because. Now we have 1x and constant minus 5. On the other side of the equation, I have x squareds that are going to pop up from the first multiplication here. A into 2x squared will give me 2a. And from my second expansion here, I'll have bx multiplied by x. So that'll get me bx squared. Combining those terms together, I'll have 2a plus b all times x squared. Now it's time to look at the linear terms, the terms just involving x. Distributing the a onto the minus 3x, I'll have negative 3a. And you can see that I need to distribute the x onto the c, so I'll also have plus c. And combining those together, my x terms will be negative 3a plus c with its coefficient. Finally, I am only going to get one constant term, and that's going to be a times positive 5. Now I've chosen to put the coefficients in different colors here for a reason. In order for the left-hand side of the equation to equal the right-hand side of the equation for all values of x, then I must have to have the same number of x squareds on both sides of the equation. I have to have 0x squareds on the left-hand side, and I have 2a plus b x squareds on the right-hand side. They must be equal in number, so that gives me an equation. And when I take a look at the x terms on both sides, I have a single x on the left. But on the right-hand side, I have negative 3a plus c as my coefficient of x. So those must be equal as well. And then constants, well, I have minus 5 on one side of the equation, and I have 5a on the other side of the equation, and those must be equal to each other as well. Since this is going to be the decomposition of that rational expression, no matter what x is, these coefficients must match. So this first method I'll call equating coefficients. We're equating coefficients of x squared, x, and constants. Now you can see I have 3 separate equations and 3 unknowns, and I can start to solve those however seems most convenient. For instance, this last equation, negative 5 equals 5a, it's pretty easy to see that a must equal negative 1. Once I know that a is equal to negative 1, then I can use that in one of the first 2 equations and solve for b or for c. In that first equation, 0 is equal to 2 times negative 1 plus b, so that means that b must be equal to positive 2. And in our second equation, 1 must be equal to negative 3 times negative 1 plus c, so that means that c must be equal to negative 2. Now that I have solved for a, b, and c, I can go back up to this important line here where I decompose it into the partial fraction forms and remove those coefficients and replace them with their actual values. As a result, I can write x minus 5 over 2x cubed minus 3x squared plus 5x as negative 1 over x plus 2x minus 2 over that same quadratic, 2x squared minus 3x plus 5. That's using the method of equating coefficients. Now there is another method that is often used as well. It's a little bit more convenient in the case where we have lots of linear factors. So let me quickly show you how you can use that as an optional strategy. In this example, I have the numerator x squared minus 1 and the denominator, which again is a cubic, which can easily be factored by taking out a common factor of x. However, this time, that quadratic can continue to be factored. Now I've got 3 linear factors in the denominator, x, x plus 1, and x minus 3, and none of them are repeated. So setting up the partial fraction forms, I'll have to use a different constant on each numerator, a over x, b over x plus 1, and c over x minus 3. I'm going to do the same initial step of multiplying by the common denominator x, x plus 1, x minus 3. When I multiply each of those terms by the common denominator, I can cancel common factors of numerator and denominator. And that leaves me with a times x plus 1, x minus 3, bx times x minus 3, and cx times x plus 1. Now once again, I could be equating coefficients just like the method I used in the last example, but I can do something maybe a little bit clever in this case. Now that I've done this step, you can see I've actually changed the domain. This particular equation is valid for any value of x. And what I'm going to do is I'm going to choose some very convenient values of x to solve for a, b, and c. Now that I have the equation in this form, I'm just going to simply choose to let x equal 0. I'll plug that in and see what equation I get as a result. On the left-hand side, I have negative 1. On the right-hand side, I have a times 0 plus 1 times 0 minus 3. Well, that's 1 times negative 3, so that's just negative 3a. Plus, when I plug 0 into the second term here, well, I'll have b times 0, and that term ends up becoming 0. And when I plug 0 in for x in the last term here, I also have 0, and I simply have negative 1 equals negative 3a. So that tells me that a is in fact just equal to 1/3. Well, I chose x equals 0 for the particular reason that I know that these last two terms here are both going to go to 0 when I plug 0 in for x. So let's try to choose a value that's going to make it easy to solve for one of the other unknowns, b or c. I'd have to choose some sort of value that if I plug in for x, most of the terms are going to go to 0. Let's try choosing x equal 3. You can see that when I plug 3 in, all of the factors x minus 3 are going to be equal to 0. On the left-hand side, I have 9 minus 1 equal to, on the right-hand side, 0 plus 0 plus c times 3 times 4, which is equal to 12c. So c is going to be 8 over 12, which is 2/3. Last but not least, I'm just going to pick one more value for x and make it so that I can solve for b easily. I don't want to choose 0 or 3, but I want to choose x equal to negative 1 in this case because that is going to end up having two of the terms become 0 wherever I see factors of x plus 1. On the left-hand side of the equation, negative 1 squared minus 1 is equal to 0. I will have 0a, I'll have 0c, but if I plug negative 1 into b, I have b times negative 1 times negative 1 minus 3. That's negative 4 times negative 1. That is going to be 4b. But if 0 equals 4b, then b must equal 0. And once again, I've got a, b, and c by coming up with three independent equations that spur off from this main equation here. Now it's simply just a matter of plugging those into the partial fraction forms so I can see what the decomposition looks like. X squared minus 1 over x cubed minus 2x squared minus 3x is equal to a over x. Well, that's 1/3 over x. I'll just write that as 1 over 3x to make things look a little more easy to read. Plus b over x plus 1, but b is equal to 0. Plus c over x minus 3. Now c is 2/3, so it might be easier to write that as 2 over 3 times x minus 3. And there we have it. That is our partial fraction decomposition of x squared minus 1 over the cubic x cubed minus 2x squared minus 3x. Now, I'll leave it up to you as to which of these two methods you prefer. Equating coefficients of constants, x, x squared, and higher powers of x is generally kind of the recommended way to go. It's going to be making the most amount of sense since, in this particular circumstance, I'm simply just choosing convenient values of x, and that's not always going to be applicable, especially if you have quadratics. You're not going to necessarily be able to find nice values of x that make most of the terms 0. So it might be good to know both ways. If you're going to look at one particular way versus another method, maybe you want to look at the equating coefficients method. So that's the method of partial fraction decomposition. On its own, it may not seem like it's super useful. We're just taking a rational expression, breaking it down into a series of other smaller rational expressions. Is that really going to be that useful? On its own, it's not really that big of a deal. But when you take a look at its applications, it's actually very important to know this method because if you have to integrate a rational expression, you may be having a real tough time trying to come up with any substitution that might work. However, if you can break that rational expression up into smaller, simpler ones, you might be able to find that you can do U substitution, or you may actually have an integral that looks like the derivative of some sort of arctangent expression. And then we can suddenly get that antiderivative and we can continue on with our integration. Same thing goes actually when you are looking at differential equations. If you're using the Laplace transform, you can end up with a lot of rational expressions, and using the inverse Laplace transform back again is not always going to be easy. So that's where you may have to take a rational expression and break it up into smaller partial fractions, and it will become a lot easier to look at those inverse Laplace transforms. Now, both of those topics really ought to be their own videos. So I'll leave it at that. Thanks for watching, and I'll see you in the next video.